Okay, I guess it's time to start. So welcome everyone. Today we are happy to have a talk by Ignacio Reyes, and he is going to speak about trace anomaly in relativistic stars. So please, you're fine to go.
Thank you very much, Dimitri, and I would like to thank all the organizers for the invitation. It's a pleasure to talk here. Okay, so what I wanted to tell you about today is based on a relatively recent paper I put on the archive. Okay, so let me start by motivating this discussion with a very simple sort of common lore or an observation that I tend to hear very often in our community, which is something related to the Planck scale and quantum field theory. So if you start with classical general relativity coupled to matter, if you rewrite the Einstein equations, in this way, obviously the stress tensor, which is this particular combination, in the equation for the stress tensor, there is one coupling that appears there, and that's just G Newton. On the other hand, if we want to do quantum field theory in curved spacetime, that is, say we add quantum corrections to these equations, in those very few cases where we can actually do the computation due to some extra symmetries, we typically learn that the expectation value of some renormalized stress tensor components look like this. So they are proportional to, there's another coupling here, and it's h bar. So whereas the classical part of the stress tensor is essentially proportional to the wait, which microphone should I turn off?
Sorry, it was mistake. Sorry.
Oh, it's good. Okay, thank you. Okay, all good. So essentially the classical stress tensor is proportional, there's the G coupling there, and it's proportional to the first power of the curvatures. The quantum version of that is proportional to h bar, and it's normally proportional to the square of the curvature. So if we just ask the question, when do these two objects, component by component, become of the same order? So if we try to generically solve this equation, obviously, if you just make this equal to this, the answer is that this can only happen when the inverse Ricci scalar, so when the curvature radius is essentially of the order of the Planck scale. In other words, if the density, let's say, of a fluid is order of the Planck density. So people normally use this as an argument to say that that means that we can neglect the effects of quantum field theory in curved spacetime if we are much below the Planck scale. So this argument is very, very simple, and the fact that it is so simple doesn't prevent it from being wrong. So
could you please explain how you compute the second line? So I would imagine that has some contributions even in flat space, right? And it depends on the matter, right? On matter.
No, of course. I'll get to this separation in a moment, because of course, what I'm calling the classical term here is obviously coming from the expectation value of a quantum operator, right? On a particular state. So what I'm referring to here, if you want to be more precise, is if you take the vacuum expectation value of this thing, so all of the dependence on the state, we call that, we throw that into the classical part of the source. So then the vacuum contributions. And this computation you can do, for instance, if you have conformally coupled matter on a conformally flat spacetime, then this results of this form hold. In general, of course, this is impossible to compute. This is just a very hand-wavy argument. Precisely what I want to show you is that this hand-waving argument is wrong. And there's a very easy way to see that this is wrong. It's wrong for different reasons, but today I'm just going to focus on one of them. Okay, so the outline of the talk is that first we're going to ask the question of when does the effects of quantum field theory in curved spacetime become macroscopic? We're going to define what that means. And then once we answer that question, we're going to look at one particular application which is related to very compact stars, close to the Buchdahl limit. So the derivation is very simple. I'm only going to use the trace anomaly in 4 dimensions. And sort of the punchline is going to be that quantum field theory in curved spacetime becomes relevant much before you reach the Planck scale. There are interesting things that happen much before you reach those densities. So now let me come back to, I think, part of your question. So if we look in general, if we do quantum field theory in curved spacetime, we can separate the total stress tensor into 2 contributions. Of course, this separation is just sort of a psychological thing, way of looking at this object. So one contribution to the stress tensor, the first term here, is what people would normally call the classical contribution. So this could be, for example, terms that explicitly break conformal symmetry already at the classical level. The most basic example of this are just massive terms. If your field has a mass, that thing breaks conformal symmetry already in the classical level. On the other hand, these are terms that they don't depend explicitly on the metric, in the sense that this is something you just plug into the Einstein equations, and then you're supposed to solve for this and find the profiles of the pressure and the density and so on. On the other hand, there are these terms which we can call quantum, but the really important thing about them is that they include the anomaly, or any anomaly that we have in the problem. Those are terms that are say, not captured by the previous term, and they explicitly depend on the metric, particularly in the case of the trace anomaly. That was what we were talking about in the previous slide. Now, of course, there is no real separation between these 2 terms, because in reality, we should think that the stress tensor, the full stress tensor, is just some expectation value of some properly normal order or renormalized stress tensor operator in quantum field theory. But we will see that in some cases, it's more convenient to absorb the state dependence into the so-called classical term. So now the statement of the Weyl anomaly, or the trace or conformal anomaly in 4 dimensions, and I'm only going to talk about 4 dimensions today, is that if we take the trace, if we consider the trace of the above object, then we're going to get 2 terms. Of course, we're going to get terms that break conformal symmetry classically, but then there's an extra contribution that is completely determined in geometric terms, and that's the trace anomaly. So in 4 dimensions, there are 2 contributions that are independent of the UV scheme for renormalization. The first one here is the square of the Weyl tensor. That comes with a central charge as a coefficient. And then there's the Euler density that comes with the other central charge of the theory. In this notation, these 2 numbers are positive, and of course, the Euler density satisfies the constraint that if you integrate it over the manifold, it gives you the Euler characteristic. There is, in principle, let me add here another term, which is of the form, say, d times the box of, so the D'Alembertian of R. But because this is UV scheme dependent, right? It depends on the scheme of renormalization. I'm just going to set this thing to 0. In principle, we're supposed to do an experiment and fix that and use that information to calculate the result of some other observable. But because the theory doesn't determine its value for now, I'm just going to assume that term is not there. I'm not saying that this coefficient is 0. I'm just going to say I'm neglecting it in this analysis.
And D is also just a positive parameter, right?
I don't. Is the sign fixed? I don't think so. Or at least I don't know an argument to fix its sign.
So what was the question?
Okay. Is it a parameter with a positive sign? You don't know the sign, but it is a constant, right?
Yeah, D is a constant, but its sign is not determined. Yeah. Okay, so with that in mind, I'm going to make some very simple assumptions to do this computation. So all I'm going to assume is that if the densities involved in our problem are much below the Planck scale, then the following three things are valid. So first, the semi-classical approximation is the correct description of the system, and that just simply means that I want to solve the Einstein equations where the metric is kept as classical, and all the quantum contributions are on the right-hand side of this equation. So again, we have a so-called classical piece and then a quantum contribution. The second and most important maybe assumption is that something about the equation of state of the classical stress tensor. So what I'm going to assume is that if you take the trace of that operator, which for a perfect fluid would be minus rho plus 3p, in general, it's just the trace. I'm going to assume that at high energies, and that means at energy scales that are much higher than the mass of the fields involved, but still much smaller than the Planck density, that this trace scales with some power. So it scales as rho to the power alpha, where alpha is strictly smaller than 1. Now you need to match in order to match the dimensions on both sides of the equation, you need to introduce some mass term, and I'm just calling that m. So alpha is some number typically from 0 to 1. The idea is that you just choose whatever theory you want, do statistical mechanics of that theory if you want, determine the density, determine the pressure, and then calculate the trace, look at how that scales at leading order at high energies, and you'll realize that the leading order vanishes. What that means is that in this trace, there is no contribution that is proportional to either rho or p. That term cancels. And then there are going to be subleading terms. And from those subleading terms, you simply read the coefficients alpha and m. So I'm going to give an example in a second, but let me anticipate. The most important example here is take the Fermi gas at 0 temperature. To give an example, for that particular system, you can calculate, you can do statistical mechanics, quantum statistical mechanics relativistically. You can find the equation of state, you take the trace, and there you will see that this thing goes as minus m squared times the square root of the density. So this is the deviation from conformality, let's say. At leading order, the trace of the stress tensor at very high energy vanishes, and that makes perfect sense because at very, very high energies, we should approach the fixed point of the conformal fixed point of the theory. But of course, there are corrections. Those corrections depend on the mass, and they scale on a particular way for different theories. In this particular case, it scales in this way. So this corresponds to the example of alpha equals 1/2. For other theories, this thing is going to give some other coefficient. But we'll come back to this example a bit later.
Sorry, could you repeat the reason why is alpha less than 1? Why is it always true?
Yes, because the reason is that at very high energies, like let's say at infinitely high energies, the theory should be approaching the fixed point of the relativization group, right? Where the beta functions vanish. That's a conformal theory. And a conformal theory, we would have that this thing should vanish, right?
Yeah, okay.
Now, if we look at theories that are not at infinite energy, this thing is going to vanish at leading order. That means that there's going to be no linear dependence on rho. That cannot appear there. But subleading corrections can appear, and that means that the power of this exponent has to be strictly less than 1.
Okay, thanks.
And a very simple example to see this in action, you can do this yourself, is just take the Fermi gas, do this computation, and this is what you get. So the last assumption is going to be that again, in this way of decomposing the contributions, the stress tensor, the anomalous terms, so those quantum contributions coming from the curvature and so on, are always subleading with respect to the fluid, so to the massive or the classical contribution. So the quantum field theory really is, we're really doing perturbation theory. Okay, so with those assumptions in mind, now we can do a very simple calculation, which is the following. So for simplicity, we said that the trace anomaly has two terms, the square of the Weyl tensor, and then it has the Euler density. Now, for simplicity, I'm going to restrict the regions where the Weyl squared is either 0 or very, very small compared to the other curvature invariants. One obvious example where this is true is, say, in cosmology. If you take an FRW metric, for example, that thing is conformally flat, so the Weyl simply vanishes there. But there are more examples, as we'll see in a moment. So that means that we can just simply forget about the contribution of the Weyl squared. So we want to now determine the value of the Euler density. That in general is very hard, but under these assumptions, it becomes very easy. One way of seeing this is that we can use the so-called Ricci decomposition that gives us the Euler class in terms of these other combination of tensors. First, it has a contribution of the Weyl squared. We just said we're going to set that to 0, so this does not contribute. And then we have the Ricci scalar squared and the Ricci tensor squared. So what we do now is that we want to evaluate this object on the background produced by the classical matter. Okay, so by background, I mean the solution to this equation, g mu nu equals a pi g t classical mu nu. Okay, that thing provides a solution. And on top of that background solution, we want to evaluate what the Euler class, what this object is. So that's very easy to do because all we need to calculate is the Ricci scalar and the square of the Ricci tensor. So let's look first at the Ricci scalar. We can just take the trace of the Einstein equations in 4 dimensions. That simply gives us this. We get the Ricci scalar on the one hand side and then the trace on the other. And via the assumptions of the previous slide, right, we assume that something about the trace of the classical, the massive contributions, and we said they scale in this way with some power alpha. So we already computed the first term. Similar thing with the Ricci scalar, with the Ricci tensor squared. So you can rewrite the Einstein equations right by throwing the Ricci scalar to the right-hand side. This is just a very simple calculation. You just take the square of the Ricci tensor. You're going to get 4 terms, right? So just to be more explicit, from this equation, we can always write this as r mu nu equals 8 pi g t mu nu, and then we throw to the right-hand side as r over 2 g mu nu, right? So I simply take that and I square it. And that's what I'm doing over here. So when we square this Ricci tensor, we're going to get 4 terms. So here, this is the massive contribution. And those are the 4 terms shown in here, right? We're going to get first the square of the stress energy tensor. That's the first term. Then we're going to get mixed terms. And the last one, for example, is going to go as the square of this term, right? Which goes as the Ricci scalar squared, and then the metric is contracted with itself. So the important thing here is that we can compare how these different contributions scale at high energies. So let's look at the first term over here, the square of the energy momentum tensor. For simplicity here, I'm just taking a perfect fluid, so something that looks like this, minus rho ppp. Okay, if we take the square of that thing and plug it into here, we get something that scales as rho squared plus 3p squared. Then we have these mixed terms, and the last term squares as rho to the power 2 alpha, precisely because of the assumptions that we talked about before. So again, at very high energies, that is much higher than the mass of the field, the first term dominates over all the other terms, okay? Because all these other terms depend on alpha. They scale with some power of alpha, and because alpha is smaller than 1, all those terms are subdominant at very high energy. So bottom line is that the most important contribution to the square of the Ricci tensor scales as g squared rho squared. I put here the pressure proportional to rho because, as we said before, at leading order, they become proportional. So I'm not interested in the coefficients and the prefactors here. I'm just trying to grasp the scaling at high energies. So with this, what does this tell us? Well, the punchline is that it's very easy to evaluate, to estimate the contribution of the anomalous part of the trace, because under the above assumptions, that's simply given by minus A times the Euler density, and the Euler density, which is given in this equation over here, its most important contribution comes from this term, and that's what's written in here. Of course, there are subleading corrections here, but they scale with smaller powers of alpha, so we're not going to care about those. Any questions so far about this? Okay, if not, let's go ahead. We just evaluated the anomalous contributions on the background given by the fluid, the classical terms. Okay, so what do we learn by doing that? Well, now we can go back to the original equations that we want.
Can I actually ask a question? So which particular model you have in mind? Because the conformal anomaly which you're talking about, that refers to some quantum field theory.
Yes.
In this curved background. Now, then you talk about density and pressure. So that presumably you have in mind some classical gas or whatever.
Right.
Finite temperature gas of photons or electrons or something like that, right?
Right. So I'm not being very...
So how the two things talk to each other? So what is the precise, how to say? Yeah, I'm trying to imagine a model which you have in mind.
Right,
so suppose we just
okay.
talk about. So suppose we just talk about Einstein theory plus Maxwell. So we consider, say, a gas of photons, and the gas of photons is quantum. It has some classical. Well, you may think of it as also having some classical limiters, some classical radiation with normal equation of state, etc. And then on top of that, you can have conformal anomaly of Maxwell theory. Is that something?
Exactly.
Yeah.
So yes, okay. So that's the idea. Here, I'm not being very precise about those details. I will be in a few slides, because the model, the one that I find most interesting in this context is just to look at the the corrections on the Chandrasekhar or the Oppenheimer-Volkoff calculation. So we start doing we consider the problem of a star made of fermions at 0 temperature. They satisfy the Fermi-Dirac distribution. So we call that the classical contribution. Of course, it's not classical because it comes, the Fermi pressure comes from the exclusion principle, right? But it satisfies, it behaves like a perfect fluid with a particular equation of state that we obtain by doing quantum statistical mechanics. We call that the classical contribution. If you solve the Einstein coupled to relativistic fermions, you get the Oppenheimer-Volkoff solutions, right? Those are well-known geometry. And on top of that, we want to add the contributions of for example, of the anomaly of the fermions in a curved space.
Okay, so yeah, maybe you proceed and then yeah. Okay,
Yes.
now I.
But it's the spirit of what you said. Yeah. Okay. So where were we? Okay.
Sorry.
So
So you consider just a plane limit. So you mean the just Minkowski background, no curved spacetime, or what particular metric you consider in here?
sorry. Is the question about what the background metric is?
Yeah.
Yes. So the background metric that I'm using, say, to do this computation is whatever the solution to the classical problem is. So, for example, if we take a gas of fermions, the classical solution is the solution of the Tolman-Oppenheimer-Volkow equations. So literally the solution that Oppenheimer and Volkow found in 1939.
So you mean like you put some right-hand side in this, so you put just some matter, and this matter determines the metric on the left-hand side?
Yes. So exactly, you start by doing that. With that, you find this metric, right? You solve these equations, you find that metric, and on top of that metric, we do a perturbative calculation of quantum field theory using the anomaly.
Okay. Good.
Yeah. Okay, thanks for the questions, because maybe the logic is a bit confusing. And now it might get a bit more confusing, because now that I evaluated something on a background metric, I go back to the original equations I wanted to solve, which were the semi-classical equations with both contributions on the right-hand side. If we take the trace of those semi-classical equations, this is what, of course, we're going to get. So now the point is the following. In the back reactive, so if you now consider the back reactive problem, where you would solve a slightly different problem, which is the Einstein equations with both the so-called classical, let's say the Fermi-Dirac contribution plus the anomalous contribution. We want to solve those equations and see how the new metric behaves. We take the trace of that equation, this is what we get. So now we have two contributions on the right-hand side, a classical contribution and the anomalous contribution. But we already know what those two contributions are, because we said we have made an assumption about the trace of the classical terms. Those scale in this way as rho to the power alpha with some massive coefficient. And then the anomalous terms, that's the computation we just did. We learned that they scale as rho squared, where rho is rho of the background fluid solution. This is a way to parameterize the problem. Now, the essential point here is that the combination of these two terms provides the Ricci scale. And it's very important here that the anomalous contributions come with the opposite sign of the classical contributions. This does not depend on any of the details of the quantum field theory. Because this sign over here, which is a minus, is fixed from the sign appearing in the conformal anomaly. So you cannot change that sign. This sign is completely fixed, meaning that the contributions to the Ricci scalar of the anomalous terms contribute with a negative sign. And that is a negative definite contribution. So basically what's happening here is that now you can think of what's happening to the Ricci scalar in this region of spacetime as the density of whatever fluid is there is increasing. So at low densities, the Ricci scalar is positive because we don't have the anomalous terms. We only have the classical contribution, and that classical contribution is positive. This is related to some of the energy conditions. But what happens is that as the density of this system increases, the negative contributions of the anomalies start kicking in until at some point they are so large that this thing vanishes and actually changes sign. So the question is, when does this happen? Because this is my criterion to decide when does the effect of quantum field theory in curved spacetime become actually important, become macroscopic, because they start competing with the classical contribution. In order to determine that, you can just put this thing equal to 0. Yes.
Can I just try to recall your logic? So you somehow you started with assuming that you can use to evaluate Ricci tensor. You use the classical contribution when you plugged it into the anomaly contribution. So you somehow already assumed that the Ricci tensor is determined just by classical Ricci tensor, right?
Yes.
So for that reason, somehow you must be in the limit where to believe this perturbation theory, you can't really assume that the second term can be a order of the first term. Is that right? Yes. Or not?
Yeah. So this is a very important point. So indeed, what I assumed is that, let's say here, for example, as you said, here, what you see is that the Ricci tensor, if you look at the components of the Ricci tensor, they are essentially given by the classical contributions. And the anomalous terms are very, very small. We don't need to use them. But that does not mean that the same is true for all combinations of all possible curvature invariants. Because there's one very particular curvature invariant, namely the Ricci scalar, which is suppressed with respect to all other combinations, precisely because this thing gets suppressed at high energies because you are approaching the conformal point of the theory. So, right, so in other words, if I go back to, I hope this helps. So if we go back to the stress tensor, the components of the stress tensor itself, right? What I'm assuming here is that I have, let's say these are two-dimensional matrices, right? So
yeah. So I guess that's your assumption. That's your main assumption. Yes. That indeed all components of matter dominate the components of anomaly contribution.
Yes,
which
exactly.
Which by no means is obvious because anomalous contribution is non-local, and yeah,
that's absolutely true. I'm sort of taking the most conservative approach possible, simply because in general we don't know how to compute those non-local terms. They're extremely hard. So I'm just pretending that they're not going to grow. I'm not saying that's true. Just saying, let's imagine that is true. And under those conditions, so the point is that if we compare component by component, the components of this matrix are much larger than the components of this matrix. For each component, however, there's one particular combination that doesn't satisfy that hierarchy, and it's precisely the trace of these two objects. So there's no hierarchy between the trace of these two things. And the reason is precisely because if you take any classical theory and you take the trace of its energy momentum tensor at high energies, you're approaching a fixed point. So the trace is vanishing at leading order. And that's a suppression that does not happen for the other combinations.
Yeah, so your main assumption is that you should have classical conformal invariance. That's your assumption somehow.
Yes, something.
Because just saying that nobody told us that you have conformal invariance at high energies. Well, that's kind of, it depends on which system we're talking about. For example, in quantum electrodynamics, there is no conformal invariance at high energy. There's no asymptotic freedom, for example. That's true in Young-Mills theory. You have you go to high energies, you get conformal points, but that's not necessarily true in general.
Yes.
But indeed, I guess what you're trying to say is that classically you have some masses are suppressed compared to momento, compared to densities, and
yes,
yeah,
yes,
so
yes, yes.
That's kind of logic.
Yes, yes. Yes. So yeah, so that means that although the components of the stress tensor, if you compare component by component, the anomalous ones are smaller than the classical ones. This is not true for the trace in general. So then you can just ask yourself, of course, at some point you need to, do the back reaction properly, but you can get a rough order of magnitude of when does this anomalous contribution to the trace become of the same order as the classical one, and that's simply when this thing vanishes. If you solve this equal to 0, the answer is not the Planck scale, as you might have naively thought, but rather this number over here. So it is the Planck density multiplied by this coefficient, prefactor. This prefactor involves the ratio of the mass appearing in your equation of state. This could be the mass of the fermion or whatever particle you have in the theory, over the Planck mass. So this is going to be a very small number, and it's raised to a positive power because alpha goes between 0 and 1. So
yeah, can I ask a question here? Sorry. You, as far as I remember, you have thrown out all the subleading terms. You mean you have put rho squared in here, but you have thrown out rho to the power of to alpha or something like this. I mean, can it affect the first term? Maybe you will have some positive terms, and it will affect the behavior for the small rho.
Right. So indeed, I threw away positive powers of rho to the alpha. That's completely true. But the point is that those powers of rho to the alpha come with a mass Planck to some negative power. So it's true that they scale in the same way as the first terms, but the coefficient is coefficient you're going to have here is much smaller.
Okay. Thanks.
So those terms that I neglected are smaller than both these terms and these terms. But we could include them if we wanted.
They're not necessarily negative. They can be also positive, right?
That's a good question. That's a very good question. Yeah. I don't know what their sign is actually, but this would be easy to check. Okay. Good point.
Okay, but anyway, they're smaller, as you say.
Yes.
The first one.
Yes. So just to give a very rough order of magnitude, if you just do this for the Fermi gas, as I said before, you just replace the mass of the electron and just put alpha equals 1/2. Then the scale, the density at which this happens is say around 30 orders of magnitude before the Planck density. So we're not, coming close to the, we're still a safe distance away from quantum gravity effects, etc. Okay, so summary so far is that if we ask the question, when do the individual components of the anomalous terms become the same order as the classical ones? In general, the answer is that this happens at the Planck scale. Of course, I put a star here because this is the most conservative point of view you could take. Certainly, if there are no local terms, they can definitely violate this, but they're so hard to calculate that I don't know what to say in that case. Now, if you ask a different question, namely, when does the trace of the anomaly become of the same order as the classical one, the answer is not the Planck scale, but something that happens much before the Planck scale, and is given by this simple expression I showed before. So then, okay.
Can I ask just something simple? Did you try to address that question in two-dimensional model? Because in 2 dimensions, you actually know much more. You can find.
That's true. I thought about this often, but my problem with 2 dimensions is that gravity is so simple / like there's no Einstein gravity, and like which maybe this is something we could discuss later, but like, I'm not sure what gravity theory I would consider.
Yeah, well, you can consider, say, gravity mixed with scalar. That's what people discuss a lot. Yeah, so there could be some model where you have modified and you multiply Einstein term by scalar, for example.
Sure. Yeah, we could do something like Jakiv-Teitelbaum over.
Yeah. Yes.
Yeah.
Or 3 dimensions. Well, 3 dimensions is not conformal anomaly, so there's nothing.
Exactly.
Yeah.
Well,
so, but maybe in 2 dimensions there were discussions of quantum effects actually with matter. Yeah, one could consider some more.
Yes.
Okay, but yeah,
it's an interesting question. Yeah.
It's an interesting question.
Yeah. Okay, so now I want to jump into what are the possible, physical implications of this, because okay, we just found some interesting, case where under a certain set of assumptions, the quantum contributions become interesting and can, become of the same order as the classical ones for the Ricci scalar. But now I need to find some physical phenomena in the universe where this thing actually becomes relevant. And that is actually surprisingly hard to find, I've realized. So if someone has ideas on this, I would be really happy to hear about them. So one application I found was the case of compact stars. And the punchline here is that this is a regime where the trace anomaly becomes interested in the Buchdahl limit. So what does this mean? So let me go back to a very important theorem of the 1950s by Buchdahl. It's very simple. It says that if you consider the problem of a static spherically symmetric and isotropic perfect fluid, okay, so the stress tensor is, as we said before, we take a static spherically symmetric metric that depends on 2 functions that we can choose like this. And then if you assume nothing about the equation of state whatsoever, only assume that the density is positive of the fluid, we're back in classical physics, that the density, the energy density, is not increasing outwards. This means that this is kind of intuitive, right? That like the energy density should be more concentrated, in the inner layers of the sphere, and that the Einstein equations hold. Then you can prove that if you take a sphere of mass m, so this is the ADM mass, the total mass of the solution, and radius RB in these coordinates, then that the condition of smoothness of the metric at the origin, so in particular, the condition that the lapse function, so the GTT component of the metric, doesn't change sign, so that the metric doesn't change its signature, right? It should always have the same signature everywhere in the manifold. That this condition implies that the ratio of the radius over the mass has to be larger or equal than 9/4 for asymptotically flat for dimensional spacetime. So the saturation of this bound, is what's usually called the Buchdahl limit. It just means that, or one of the things that it means is that beyond this point, there are no static solutions to the Einstein equations under these assumptions. Now, this is a very sort of global characterization of the problem in terms of the total mass and the radius of the sphere. But a more local characterization of the Buchdahl limit is really the point where I think is the very interesting idea is that the Buchdahl limit is the point where the metric at the origin becomes degenerate because the lapse function goes to 0. In other words, the redshift that you have, from the origin to any point outside, it just goes to infinity. So one thing that is a very intuitive and very interesting is to look at is, for example, you can consider what you do for the case of black holes. You define a tortoise coordinate, which you just define in the standard way, using the 2 functions that appear in the metric. So you're gluing this fluid solution to a vacuum outside, In the exterior, you can solve, you can find, you can just integrate this equation for the Schwarzschild vacuum solution, and you just find this usual thing. The thing to notice for this solution for black holes is that, this is of course very well known, that if you take the radius going to the horizon, the tortoise coordinate opens all the way up to -infinity. The horizon is located, at that region where our star goes to -infinity. So the observation is that the same thing happens actually, not for black holes, but for stars that are approaching the Buchdahl limit. Because in those cases, as I just said, the lapse function, which determines, say, if you look at the behavior of the tortoise coordinate close to the origin, the leading term goes as 1 over the square root of the lapse function of the origin. So when that thing goes to 0, that's the Buchdahl limit, this thing goes to infinity, such that again, the range of the tortoise coordinate opens all the way on the real line. So in other words, it's like the physics somehow of the geometry of the near horizon region of a black hole is very similar to the physics happening near the origin of a star that is approaching its Buchdahl limit. So finally, let's go back to the concrete example we were looking at. Again, for cold fermions, you can just do quantum statistical mechanics, look at the density of states, you take the Fermi-Dirac distribution, you go to low temperatures, and then you could just find what the equation of state is in different regimes. And let me skip these details in view of time. The point is that if you look at that equation of state at very high energies, this thing has the behavior that we were talking about before. So if you take trace rho minus 3p, the thing scales with some power, rho to the alpha, where alpha is equal to 1/2 in this particular example. Now, again, for the particular case of the star made of fermions, you can actually go a bit further, because if you look at the continuity equation for this problem, the divergence of the anomaly, so the quantum terms, vanishes identically. That's just an identity, which means that the continuity equation for the system is the same as the classical version, which is this thing over here. This is one of the TOV equations. The interesting thing, though, is that you can actually solve this equation analytically for the Fermi-Dirac distribution. Let me spare all the details. The result that you get, you just need to perform a very simple integral. The result that you get at leading order is this. So this, again, if you take the Dirac at 0 temperature, this gives a relation between the redshift, so the value of the lapse function at the origin, which is becoming very, very small, as we said in the Buchdahl limit, and the central density, which is becoming very, very large in the Buchdahl limit, right? So this equation really characterizes the Buchdahl limit. As the central density goes to infinity, the lapse function at the origin goes to 0, and the redshift, towards the origin is going to infinity. So this is one very particular example where you can actually solve things analytically. It's very nice. So finally, let's go back to the anomaly. Again, under the same assumptions that we've been talking about, static and spherically symmetric problem of a star. This is the stress tensor, the classical stress tensor, this is the metric. One of the requirements that I had for my calculation of the trace anomaly is, a long time ago, I told you I needed the Weil squared vanishes for simplicity. And that actually happens here, it happens at the origin. This is because if you impose regularity of the metric at the origin, the metric has to be, you have to have local flatness here at the origin, and you can very easily check that although the Weil tensor does not vanish at the origin, its square vanishes identically at the origin. So that means that this assumption that I had made before to do my calculation is valid at the origin. It's actually valid in a neighborhood of the origin. So all the results that I had for the trace anomaly are valid for some neighborhood around the origin of the star. So finally, the physical effect that I found that was interesting was if you have the star, if you look at the wave equation, for example, of a scalar field. So consider now an external field. So we have the star made of fermions that has quantum and anomalous contributions. But now imagine that on top of that, there's some probe field. This is some other field. Let's consider a minimally coupled massless scalar. If you put that on this particular background, this is very well known. You just decompose, you separate variables, and that leads to a Schrodinger equation in the torus coordinate, where there is some particular effective potential that depends on the metric. So in general, it's very hard to compute the components of the metric, the back-reacted components, right? That's also an impossible task. But fortunately, or miraculously, there is one particular point of the spacetime where we can actually evaluate this potential, which is if I consider only the S wave, so I put the angular momentum to 0, this term drops, so I can evaluate it at the origin, r equals 0. So if I do that, it's not obvious from this expression, but believe me, if you do that, what you get is this thing over here. It's simply the potential at the center of the star is proportional to the lapse function there and the Ricci scalar. And I say that this is sort of miraculous because it happens to depend on the Ricci scalar, which is the only thing that I can actually compute from the trace anomaly. So that means we were lucky because we have the back-reacted version of this object over here. So finally, what's the result of all of this? So forget for 1 second about this equation. Just look at this plot. So here we have the potential for L equals 0 as a function of the radius. Here is the surface of the star. So this is the potential for a scalar, just in the Schwarzschild vacuum geometry. That's the exterior of the star. This is the interior of the star. So generically, the potential is sort of trapping, right? Because it's attracting waves. This is just a schematic representation of this. And then it somehow matches, the value at the surface, and then it drops to infinity. So although it's very hard to compute the specific form of the potential everywhere inside the star, we have one data point, namely that, as I just explained, we know how to evaluate its, the potential exactly at the origin, okay? And that's given by this thing over here. So now I can directly evaluate this because in the particular example I told you, the lapse function I get by the Fermi-Dirac distribution, right? That's this behavior as sort of m squared over the square root of the density. That just comes from solving continuity equation. So the first term we have, and that's what's contained in here. So this term over here. And on the other hand, we have the Ricci scalar, but the Ricci scalar, including the anomaly, we already did that computation, is given by this, okay, where I just fixed alpha to be 1/2. Right, so remember that these were the classical contributions of the fluid, and these were the anomalous contributions. So what do we learn with this result? So first, imagine that the density is very small, or in other words, that we can neglect the anomalous contributions. So that means we can neglect this term over here. The only thing that contributes is the first term. Now you see there's a minus in front of here, which came from the minus here. So that means that the value of the potential at the center, classically, so with no anomaly, is negative. let's say it's somewhere here. And then the potential goes up and matches at the surface of the star. What is the role of the anomaly? So now, as the densities become higher and higher, what happens is that now this term becomes important. As we said before, this comes with a minus sign, which together with this minus sign gives a positive contribution to the potential, and that moves this minimum upward. Exactly where does it move it? Well, it depends on the density. But the sort of the rough physical picture is that what's the role of the anomaly is that it's moving the potential, at least at the center, it's moving upwards. So somehow it's making it less attractive for the scalar field. So finally, just to get an order of magnitude of sort of the physics involved, if you look here, this value of the potential has an associated frequency, because in the Schrodinger equation, right, we have the potential on one hand side and the frequency squared on the other. So we can sort of estimate this window of frequencies where the anomaly is changing. The anomaly is changing the sort of the spectrum of this operator, by which amount, or we can determine an order of magnitude for those frequencies is given by simply this value. Okay, and this value is simply given by this number over here. That comes directly from this equation. So here you have to plug in back the, the h bars and the speed of light. And once you do that, this is related to sort of the Compton wavelength of the particle involved. If we choose the electron, again, for this particular example, what you see is that this window of frequencies is the order of seconds. So sort of the point that I'm trying to make here is that although the energy scales involved, the values of rho at the center of the star are unimaginably high. This is like, getting close to the Planck scale. The physics that an outside observer sees asymptotically, for example, in terms of the spectrum of the quasi-bound states of this problem, if they do, if you were to do a scattering experiment with waves from very far away, even though the energies scales of the physics going on inside the star are incredibly high, still an outside observer can make measurements and detect this effect, by very sort of making experiments at low energies that involve, the scale of seconds and so on. And this is again related to the fact that the redshift is very large. Okay, so that's it. Let me conclude. So we discussed that the effects of the trace anomaly become macroscopic. That is, they compete with the classical terms, not at the Planck scale, but at some other scale that is given by this particular result. That depends on two numbers, some real number between 0 and 1, and then some mass parameter. Those two numbers, you simply read them off of the equation of state at high energies of whatever theory you have. Of course, under the assumptions that I made. The essential result is that what happens at these scales is that the Ricci scalar becomes negative. The fact that it's negative comes directly from the sign of the Euler class appearing in the trace anomaly. For the particular case of, looking at scalar perturbations of stars close to the Buchdahl limit, we saw that the anomaly controls the spectrum of these sort of low frequency modes. And morally speaking, the object becomes less attractive for minimally coupled fields because the potential tends to move upwards. So as an outlook, I looked at the spin equals 0 problem, but we could study spin 1/2, spin 1, spin 2 perturbations, and so on, and see if there's any interesting physics there. And I think more importantly, the question would be for me is like, okay, how are these ideas in any way related to the problem of gravitational collapse? So those are some things that I find interesting. And yeah, that's it. Thank you very much.
Thank you. Are there any questions?
Yeah, maybe I would like to ask a question. So if in the final example you consider like the small density and you consider high density, so what kind of physical process should I have in mind when we compare this kind of density? So maybe you should you mentioned gravitational collapse. Is it the physical process I should imagine? So we have a star with a small density, then we have a star with big density, and we see how the behavior changes completely when we increase the mass of a star or something like this.
I think that's a possible example to consider. Now, the thing about gravitational collapse is that normally the standard paradigm of gravitational collapse is the Oppenheimer-Snyder model, right? Where you solve, so the T mu nu that you take is, minus rho 0, 0, 0. So the pressure is 0. The result of that is that you get a Penrose diagram, it's a system that looks like this, where you have a star collapsing, right? This is the surface of the star. And in a finite proper time, it creates a space-like singularity, blah, blah, blah. For this particular case, what I'm talking about does not apply because the Oppenheimer-Snyder stress tensor violates one of the assumptions that I made. Namely, that if you take this trace, right, you get minus rho plus 0. This thing could not be further away from being conformal, right? So I would say for very fast gravitational collapse, which is the reigning paradigm in this, in general relativity, if gravitational collapse happens very fast in this way, then what I'm talking about plays absolutely no role. I think so. However, if you consider a different form of gravitational collapse, say very slow gravitational collapse, adiabatic collapse, then the physics is completely different, because then you have I don't know how to draw this really, the Penrose diagram, but like Penrose diagram looks something like this. This relates to the Buchdahl theorem. So let's consider now the example you said. So we have a star. Let me draw it like this. So this would be like the Penrose diagram of a star, let's say at constant radius. But now you imagine something that is slowly decreasing its radius, but very slowly. And the endpoint of this evolution, right? So now we would have, for example, the density here at the surface of the star is going to be low, but the density at the origin, at the center, can be very high. That's what you said. So at some point, at some finite proper time, this thing is going to develop a singularity, but a very different kind of singularity, because at some point you're going to reach the Buchdahl limit, right, where the metric becomes singular, but at the origin. So you create a sort of a time-like singularity. So what I'm trying to say here is that I'm not sure if what I talked about today actually applies to gravitational collapse. For the standard sort of paradigm of very fast gravitational collapse, I think it does not. But if there is some process in the universe where gravitational collapse occurs very slowly, I think that's another story, and then this would play a role.
Okay, thank you. And then also have another question. So you consider two particular situations when you compare the Ricci tensor of classical one and coming from anomaly, and you also compare the Ricci scalar, classical one, and coming from anomaly, and you compare the magnitudes, and you say that something important happens when the classical one gets of the same magnitude at the coming from anomaly. But can you explain again why it is important when they become equal or of the same magnitude, and what's the difference between these two situations when you consider a Ricci tensor, when you consider Ricci scalar?
Yeah. Okay. So these are two different questions, I guess. So okay, let me go back. Okay, let me start with your first question. So just consider the Ricci scalar for now. Let's forget about the Ricci tensor. So in the Ricci scalar, we have these two contributions, and the point I'm trying to make is that normally at low densities, for non-extreme phenomena in the universe, this thing is going to be vanishingly small. It's going to be so small that you don't even care about putting into the semi-classical equations because everything is dominated by the classical piece. And this contribution is positive. That means the Ricci scalar is positive. Now, then we see that there's some contribution coming from the anomaly that comes with the opposite sign. So as a sort of a loose way of saying when does the anomaly become macroscopic, I'm just defining it loosely as when these two become of the same order. That doesn't mean that there is something necessarily that there's some physical effect happening there, right? That is kind of a question. One physical effect that I talked about at the end was, the propagation of a scalar field, because that thing is sensitive. The potential at the origin is sensitive to the sign of this thing. So if the anomaly becomes important, this thing changes sign, and then the potential can become positive or negative depending where you are, and that affects, what an asymptotic observer can see if they do scattering of scalar waves. I'm not saying that like it's somewhat arbitrary to define what the interesting point is, because maybe it's not necessarily when they become equal, but it just means that you cannot neglect these terms anymore into the computation of the Ricci scalar. Maybe that's the more precise way of saying.
So you mean what you're trying to make? So when you consider high densities, you say that anomalies are important, and you kind of trying to estimate how it is important.
Yes.
Yeah, and the second question was about what's the difference between comparing the Ricci scalars and Ricci tensors.
Yes. So so let's see. Let's go back here. So here in the first line we have the Ricci scalar, and the second one we have the Ricci tensor square. So let's look at the Ricci scalar. The point is that these two objects behave in a very different way, because the Ricci scalar at the classical level it's suppressed because it's related to the trace. It's determined uniquely by the trace, and that trace is suppressed because at high energies, you have this thing that rho becomes approximately equal to 3p. And then there are subleading terms, but those subleadings are suppressed because the highest power that appears here is rho to the alpha. And the reason is because the Ricci scalar is determined precisely by the combination, let me write it here, by this combination rho minus 3p. But this combination is suppressed because at very high energies, this thing essentially behaves like radiation. So rho is equal to 3p, like a conformal field theory, right? So that means that the Ricci scalar on the background is suppressed with, its sort of natural value. So it scales as rho to the alpha. Alpha is gives you the leading contribution to R. But now if you look at the Ricci tensor squared, so, okay, and just to finish here, that means that the Ricci, consider then how the Ricci squared behaves. This thing behaves as rho to the power 2 alpha, right?
Yeah, okay.
Now consider in contrast the Ricci tensor squared. So the Ricci tensor squared has these different contributions. Okay, these come from just rewriting the Ricci tensor in the Einstein equation like this. And here this cancellation happens, but it doesn't happen for all those terms, sort of this suppression, because you see in the Ricci tensor square, there are contributions that are, say, proportional to the Ricci scalar square, and those are suppressed because alpha gives you that term. But there are also terms that have nothing to do with the trace. So if you want, you see these terms that go with the square of the stress tensor itself, they have nothing to do with rho minus 3p squared, right? That's the combination that is suppressed. That's the one that enters here. But the combination that enters here is just rho squared plus 3p squared, and that thing doesn't vanish for a conformal field theory. So this term, is not suppressed by alpha, meaning that the leading order in the Ricci tensor has nothing to do with alpha. Those are corrections. So this one is not suppressed.
Okay, so we're trying to say that when you consider Ricci scalar, you have an interesting behavior because of the suppression compared to the anomaly, which is not suppressed.
Yes.
But when you consider the Ricci tensor, you probably do not have suppression nor in the scalar, nor in the classical case, nor in the anomaly case. So you have the quantities of the same order. It's not very interesting, but you want to consider when you have a classical part much less than the anomaly part. Classical part suppressed, but anomaly part not suppressed. So you want to consider this kind of situation.
Yes, and that only shows up in the Ricci scalar. It doesn't show up in the other curvature.
Okay, thank you.
I have a comment unrelated, but in principle there were discussions of the effect of conformal anomaly on cosmology. So in the cosmological setting, you may assume spherical, you may assume homogeneity and kind of spherical symmetry, and then conform. Essentially, the scaling factor plays the role, and then you can determine the effect of conformal anomaly. So in principle, you can try to see whether the similar effects can happen where anomaly is
so that's a very
I'm just saying there were papers, I think, but I don't remember details, but Matola in particular, Antoniadis Matola, they studied the effect of conformal anomaly in cosmology.
Right. So actually, as far as I understand, this is precisely what Starowinsky inflation was, in its earlier formulation, right? Then you can write it as a, in some other language. But the thing that in the case of Starowinsky, I think that for the Starowinsky inflation, like this term played a very important role, and this is precisely the term I want to get rid of.
So exactly. So that was the term, which is just R squared term, which you add to the Lagrangian with.
Exactly.
Yeah. So calling it conformal anomaly is a little misnomer, but it's just R squared term. But you can actually integrate the other terms. Well, you can find the contribution of other terms in the part of effective action, which depends on conformal.
Certainly. So I actually thought about this problem. It was the first thing that came into mind, because then the Weyl tensor is zero everywhere, right? So it's an even better case. The thing what I wasn't able to find, but if someone has an idea, I would be like really happy to hear about it. That what I didn't find was an application. in the sense that if you look at, for example, like why did I become interested, or one of the reasons why I became interested of the case of the Buchdahl limit in stars is because of this funny effect that if you calculate the potential at the origin, this thing happens to be proportional to the Ricci scalar. And because the Ricci scalar is dominated by the anomaly, then you have something interesting. But what I did not find is, for example, if I solve simply the wave equation of a scalar in an FRW system, then the wave equation, there's like no obvious dependence on the Ricci. It's like I couldn't identify any sort of physical observable in that scenario that was sensitive specifically and only to the Ricci scalar.
Yes, I guess the mechanism can be different. Yeah, but yeah, I don't have anything to say.
But I'm not saying it doesn't exist. It's just that I haven't been able to find it. But that would be a really interesting example. Yeah.
Okay, thank you very much. Yes, so I guess we probably need to stop now. Yeah, I'm not sure.
Super.
Yeah, thank you much.
Okay, thank you so much. Thanks for the questions.